Good afternoon, everyone. It's a pleasure to have one of my own students giving a talk today. I don't need to read something about you. I know everything that I want to say about you. Benjamin graduated from KNN, right? Yes, I'm sorry, okay. KNN, University of Science and Technology, Kumasi, Ghana in 2018. And since then, he joined our PhD program, and he's doing his PhD under the auspices of transportation technology, basically. So his research interests include machine learning, optimization, and mobility in demand. So with further ado, I'd like to introduce him, and I'd like him to come and give his presentation. And by the way, I think you're going to find his presentation very interesting. With that, go ahead.
Thank you very much for the introduction. Okay, so to drop off. So I said my name is Benjamin Lartey, and my advisor is Dr. Maifa, and my co-advisor is Dr. Karimudini. So the title of my talk is an efficient and scalable profit-aware vehicle dispatch framework for ride sharing. So to start with, I will first provide an outline of my presentation. First of all, I'll briefly introduce the subject and also talk about some technologies that we use. And then I'll provide the motivation behind the work, the objective and technical challenges, and some preliminary concepts where we talk about two main badge assignment methods, which is multiple badge assignment and a single request badge assignment method. And then I'll also provide a detailed description of our proposed framework, and then the experimental study and some miscellaneous work that we've also done. And then I will talk about the conclusion and future work. So to start with, an on-demand ride-sharing system simply consists of a some number of vehicles, a set of vehicles, and a set of requests. So requests are sent to a dispatch server, and then the dispatch server assigns the request to vehicles. And the idea behind ride-sharing is to assign requests which are traveling in a similar direction to the same vehicle. So I've provided a very simple scenario here to explain the ride-sharing method. So in this scenario, or the figure that you're seeing there, we have 4 requests, and then we have 2 vehicles. So we want to assign the 4 requests to the 2 vehicles. So in this particular scenario, requests 1 and 4 are assigned to vehicle 1, and then requests 2 and 3 are assigned to vehicle 2. And vehicle 1 follows this schedule or this order to pick up and then drop off the request. It first picks up request 1, then request 4, then to drop off request 1 first, and then followed by request 4. In a similar manner, vehicle 2 picks up request 2 first, then followed by request 3, and then to drop off 3 first, and then 2 second. So to continue, we will provide some basic terminologies that we use in this particular work. The first one is road network. So in this work, we define road network to be denoted as an undirected graph, saying where the graph has a set of vertices, which we denote as n, and then an edge set which we are denoting as a. And then for each edge, say A and B, is associated with a certain travel cost, which can be time, distance, or profit. And then we also define a passenger as a pass request that has been picked up by a vehicle and is on its way to its destination. And then we define a trip also as a set of requests that can be merged through ride sharing and served by a single vehicle. And then we also define a schedule as the order in which a vehicle will pick up a request and then drop off the request. And we define waiting time as the difference between the actual pickup time and the request, or the time the request was sent. And we also define total travel delay as the difference between the actual drop-off time and then the traveling alone time, or when the passenger is traveling alone without sharing the ride with others. So these are some few technologies that we all need to be aware of when it comes to this particular work. So moving on to the motivation of this work, or what actually motivated us to work on this particular research. is that there is an increase in personal mobility. As we all know, in this age, everybody wants to own a car. Everybody wants to own a private car. And because all of us want to own a car, it has contributed to some serious transportation-related issues, which includes like traffic congestion, environmental pollution, and then parking space availability. So to address some of these, transportation-related issues, there have been several work or research that have been done to address these issues. So one of them is on-demand ride-sharing, which is the focus of our presentation or talk. And then with regards to the benefit that companies or industries obtain from ride-sharing, companies like Uber and Lyft are able to make more profit by serving more requests with the same number of available vehicles. And then with regards to the passenger or the ride-sharing user, they are able to pay less amount of money because they are able to share the trip cost with other people. But though this ride-sharing technique helps to address transportation-related issues like traffic congestion and environmental pollution and parking space availability, the problem is not easy to solve. So there are some technical challenges associated with this problem. The first one is that the ride-sharing problem is by nature ride-sharing problem by nature involves a very large number of requests and then vehicles. So this actually leads to a very serious issue where the search space of the ride-sharing accommodations and then the route grows exponentially as the number of requests or the capacity of the vehicle increases. And then also passengers or people are usually sensitive to the time of service. People wish once they submit their request for a ride, their request will be attended to immediately, and then they'll get a vehicle, and then they'll be picked up and dropped off at their various destinations. And then finally, the ride-sharing problem is so dynamic in the sense that you do not receive all the requests at a go. We do not have a full knowledge of the requests. The requests are coming to us at different times. So how will we be able to capture that? And then because the requests are coming to us at different times, being able to find an optimal assignment at a certain particular time does not necessarily guarantee that particular assignment will be optimal in the future. So to address these technical challenges, we have these two main objectives. The first one is to formulate the ride-sharing problem as a constrained assignment optimization, as a profit-aware problem. And then we also propose a vehicle dispatch framework, which is computationally efficient, because we introduce a certain method called feasible schedule pruning, which helps to reduce the search space of the ride-sharing problem, and by so doing helps to make the algorithm very efficient. So the next thing is to talk about some preliminary concepts. As I stated in the outline of my presentation, that we are considering a badge assignment, and there are two badge assignments. We have multiple badge assignment and then single request badge assignment. So I want to provide a distinction between the multiple badge assignment and then the single request badge assignment. So the first one is multiple badge assignment. So in this scenario example, we are considering requests being submitted over different time steps. So time step 1, 2, and then 3. So in total, 9 requests will be submitted, but for each time step, 3 requests are submitted. And then we have 3 vehicles available to us. So what multiple badge assignment does is, once the requests are submitted, it finds different groups of the requests. So for instance, in this example, it groups the first 3 requests that have been submitted, request 1, 2, and 3, and then assigns them to vehicle 1. So in the next time step, requests 4, 5, and 6 are also submitted. And then it groups the request 4, 5, and 6 and assigns it to vehicle 2. And then finally, in the last time step, requests 7, 8, and 9 are also submitted. And then it groups, multiple badge assignment groups the requests 7, 8, and 9 and assigns them to vehicle 3. So the difference between the multiple badge assignment and the single request badge assignment, which our method is based, the foundation of our method is a single request badge assignment. In the single request badge assignment, just as the previous method, requests are being submitted over different time steps. Requests are being submitted over different time steps. But for single request badge assignment, once the requests are submitted, we are assigning the request to a vehicle in a one-to-one fashion or one-to-one manner. So for instance, in this figure, request 1 is assigned to vehicle 1, request 2 to vehicle 2, request 3 to vehicle 3 for time step 1. And then in time step 2, we assign another set of 3 requests are submitted, request 4, 5, and 6, where we have 6 assigned to 1, 4 assigned to vehicle 2, and then request 5 to vehicle 3. And then in the last time step, another set of requests are submitted, 8, 7, and 9, where we have request 9 assigned to vehicle 1, request 8 assigned to vehicle 2, and then request 7 assigned to vehicle 3. So to summarize the difference between the multiple badge assignment and the single request badge assignment, basically multiple badge assignment, a set of requests are submitted. When the requests are submitted, find different groups of requests before assigning them to the vehicle. But for single request badge assignment, assign the request to the vehicles in a one-to-one fashion. But keep in mind, despite single request badge assignment assigning requests to vehicles in a one-to-one fashion, the main purpose of ride sharing, which is sharing the ride with other people, is not missed. Because we are, like for instance, in this example, the last figure, the figure 3, at the end you have three requests assigned to vehicle 1. Just like in the previous, in the multiple badge assignment, you have 3 requests assigned to vehicle 1 at the last time step 3. So we are not losing the value or the idea behind ride sharing. So moving on to the proposed framework, I will first start with an overview of our proposed framework. So to start with, we have a set of requests are submitted periodically, let's say every 30 seconds, some number of requests. People request for ride for, let's say, every 30 seconds. And then within our system, we have available number of vehicles. Then all the requests that are submitted, you put them in a pool. And then based on the vehicles availability, we look for different combinations of requests to vehicles, which we call, I will explain down in the next slide, which we call request vehicle graph. So we find different combinations of requests to vehicles that can serve the request. And then we look for the feasible schedules for each of the request vehicle groupings that we have. And then these feasible schedules will determine whether the schedule is feasible or not. So all schedules that are infeasible, we reject all schedules that are infeasible, and schedules that are feasible, we put them in a pool. So the idea behind this is a feasible schedule pruning. So the idea behind this method is we want to filter out unnecessary schedules, because we want to reduce the solution space that will be fed into the integer linear program assignment. So we are using this feasible schedule pruning strategy to reduce the solution space for the integer linear program. And that helps the method to be very efficient, as you will see in the experimentation. So I'm going to talk about each of the blocks in the proposed framework. So the first one is the request vehicle graph. And the request vehicle graph is responsible for computing different combinations of requests and vehicles that can be pairwise shared. And we said 2 requests can be grouped together or are connected, provided those 2 requests can be served by the same vehicle. And then the vehicle and the request are also connected, provided that the request can serve the vehicle can serve that request. So as you can see in the algorithm on your right, as you can see on the algorithm on the right, algorithm 2 and line 4, we check whether the request is connected to the vehicle or the vehicle can serve the request. If that's the case, then we add that particular combination to our request vehicle graph. So as you can see in line 5, once line 4 is satisfied, which means the request can be served by that vehicle, then add that combination of the request and vehicle to our request vehicle graph. Then The next step is to find, after we've computed the different request vehicle graphs or different combinations of request vehicles. The next step is to find the schedules of each of the combinations and then find the feasible ones. So to find the feasible schedules, we based on these three constraints. So each of the schedules which are considered to be feasible are supposed to satisfy these three constraints. The first one being the waiting time. So we don't want the waiting time to exceed a certain threshold, which we are calling omega in this instance. And then the total travel delay should also not exceed a certain total travel delay, which in this instance is delta. And then the capacity, we don't want to exceed the capacity of the vehicle. If the vehicle can take up to 4 people, we don't want to that capacity or the force should be exceeded. So we consider these constraints to determine whether a schedule is feasible or not. So this is the algorithmic breakdown of the feasible schedule pruning strategy. So first of all, like in the algorithm 1, where we first have the request vehicle graph, as I demonstrated in the proposed framework. Then in line 2 of algorithm 1, we are finding the feasible schedules. And then in line 3, we are feeding the feasible schedules into an integer linear program, which I will talk about in the upcoming slides. So we feed the feasible schedules into the integer linear program. Then we find the best assignment of schedules to the vehicles. And then algorithm 3 describes the feasible schedule computing strategy that we've considered. So in line 5 of algorithm 3, before before a request will be included into the schedule of a vehicle, we check whether when the request is included into the schedule of that vehicle, based on algorithm 2, is that going to violate the constraints or not? So based on that, then we determine that this schedule for the vehicle is feasible or not. So this strategy is helping us to reduce the solution space that will be fed into the integer linear program. So this is the integer linear program that we've considered. And our objective is to maximize the overall profit as shown in equation 1. And then we are considering two constraints, constraint 2 and then constraint 3. So constraint 2 ensures that we don't assign more than one schedule to a vehicle. And constraint 3 ensures that we don't assign a request to more than one vehicle. And as I said, our focus is to maximize the profit. And the profit is given by the fare that each request is going to pay. So if you have a vehicle and then there are 4 people, the fare that each of the passengers are going to pay. And then we also consider a certain compensation. So if we don't, if you are not able to get to the origin of the request, we compensate the request. So let's say you request for a ride and you expect me to get it in 2 minutes and I get it in 3 minutes. So I'm going to compensate you. Basically, that's the idea behind it. And then we subtract the cost. We subtract the cost of operating the vehicle, like you buy gas and all those kind of things, from the total amount of money that the driver or the vehicle makes from the passengers within the car. And then the total profit is given by summing all the profit that are obtained from each of the vehicles. So based on these formulations, our framework or our proposed approach is called the single request budget assignment with travel time considerations, which can be abbreviated as SRB80.
Would you repeat your constraint 2 and 3?
So constraint 2 is ensures that the schedule, we don't assign more than one schedule to a vehicle, because eventually you just want to have one schedule to be assigned to a vehicle. And then and then 2, you don't want to assign a request to more than one vehicle. So the next thing is the experimental study, some experiment that we've performed. So in this presentation, we've shown some part of the experiment, and then the others, I've put my contact there, so in case you don't get something, you can contact me. So first of all, let me provide a brief description of the data set. So this data set is a large public data set which was obtained from New York City, Manhattan to be specific. And then the data has over 1 million instances. And the prominent features are the pickup and drop-off dates, pickup and drop-off locations, trip distances, and driver recorded passenger counts. And then the reason why we consider this data is primarily because the data has been widely used in the literature when it comes to ride sharing. And then also, since the data includes a large number of requests, it will be very good to test for the scalability of the algorithms.
Could you talk what is scalability? Know what scalability is, but many people, they may not know.
So scalability in this instance is with regards to algorithms, when you are increasing the problem instance, or your problem is growing in size, will the algorithm be able to handle the growth in the problem, like the problem size? So basically, that's the idea behind the scalability. So you want to check whether, if I go from, let's say, a problem size of 10 to a problem size of 10,000, will my algorithm be efficient, or will it be able to still provide me with solutions within a reasonable amount of time? So usually some algorithms become intractable when the problem size becomes very large. So that's the idea behind the scalability you're talking about. So the next thing we did is we considered various parameters: the maximum waiting time, the batch period. So maximum waiting time, the maximum waiting time that a passenger is willing to wait. Then the batch period is the time allowed for requests to be submitted to the system. And then capacity is the capacity of the vehicle. And then instance scale is the problem size. So we are varying the number of requests from like 400,000, the number of vehicles is 2,000. And when the number of requests is 600,000, the number of vehicles is 2,800. And the number of requests is 800,000, 3,600. And then finally, very large problem size, which is over 1 million requests and then 10,000 vehicles. And then for the maximum waiting time, we vary from 120 seconds to 180 to 240 to 300 seconds. And batch period will vary from 5, 10, 30 to 60 seconds. And the vehicle capacity from 2.4 to 2.46 and then 8.
So you're assuming a different type of vehicle to be available.
Yeah, different capacity, vehicle size. So we compared our approach to 4 main methods. We compared our approach to a single batch assignment method, and then to a multiple batch assignment method, and then to a greedy method. So the first one is the single request batch assignment to travel, considering travel distance, is a single batch assignment method. And then the greedy method is a greedy insertion method, where they assign the request to the vehicles. They assign the request to the nearest vehicles. And then you also have a request to vehicle, and then optimal schedule pool algorithm, which are based on multiple batch assignment. So we compare our method to these 4 methods. So the first part of our result is when we are varying the maximum waiting time. So here we are varying the maximum waiting time from 120 seconds to 180, 240, and then 300. And then we look at the behavior of the algorithms. So as you can see, our method is the SRB80, which is the one in blue. And then the state-of-the-art method is OSP, which is called optimal schedule pool. And then you also have the greedy insertion method, which is the green one, and then request strip vehicle method, which is the red one. And then we have the single request batch assignment with travel distance consideration, which is the brown one. So as you can see, when we increase the maximum waiting time, the profit generated is also increasing accordingly. And the reason is that once passengers are willing to wait for a couple of minutes, then that means we'll be able to provide services to more people. And by so doing, we're able to make more profit. So that's the reason behind the increment of the profit generated over different maximum waiting time. And then in a similar manner, the response time or the computational time is also increasing when we are increasing the maximum waiting time. And then you can see that the black one, which is the state-of-the-art method, and then the RTV, which is the red one, which is a multiple batch assignment method. The OSP, this is a state-of-the-art method, and then RTV is these two methods are multiple batch assignment method. So because they are grouping, because they group the requests before they assign it to the vehicles, that actually affects their computational time. And their computational time increases over different maximum waiting, over when we vary the maximum waiting time. And then in the profit generated figure, you can see that the OSP has it generates more profit than our method. However, this response time is very bad. As you can see on this bar, that's the longest bar. The black bar is the longest bar here. So the response time for the optimal schedule pool algorithm, which is a state-of-the-art method, is way longer than our method, which means it's taking so much time to be able to generate this amount of profit. So our idea or our goal is to come up with a method that provides a balance between the amount of profit that is generated and then the response time. So basically, that is the goal. That's the idea behind our method. So the next thing is you also vary the vehicle capacity. So we change the vehicle capacity from 2, 4, 6 to 8. So in a similar manner, just like the maximum waiting time, the amount of profit that is generated is also increasing because we have, of course, more seats, and therefore we are able to provide services to more people. But the response time for the multiple batch assignment method, and then the response time for the multiple batch assignment methods, which is the RTV and then the OSP, is way longer, or is computationally expensive as compared to our method, which is a single request batch assignment with travel time considerations, which is the SRB80. And then in a similar manner, we also vary the fleet size. So fleet size is the number of vehicles. So we change the number of vehicles from 1,000, 2,000 to 3,000. And in the same way, all the 5 methods, the profit that is generated is increasing because you have more vehicles to provide services to people. And then the response time for our method, and then the grid insertion method, and then the other single request batch assignment method are way better than that of the multiple batch assignment method, which is the red and then the black one.
How do you control the number of fleet size? Because at some point, you cannot just continue increasing the fleet size. You have to also look the other side of the problem. You have to find the break-even point where it makes sense to bring 100 vehicles versus 150 vehicles versus 200 versus 3,000 vehicles for a given estimated number of passengers.
Yeah, so that's a very good question. So that is one analysis that we can do, but that's not the main focus here. We can be increasing the fleet size from, as you are saying, from 1,000, 2,000, 3,000, 4,000, and then and so on and so forth. So I believe if we should do an experiment like that, we'll get to a point that the amount of profit being generated is not going to change. It may even be decreasing, and that will also be affecting the response time.
What I am suggesting, I know what you have done, but to make your experimental result meaningful, and say that, yes, this one goes, it comes as close as what people do in the real time is beforehand, you got to know your upper limit based on some criteria, and then to say that, okay, the result that I have, it makes sense or not. You see, right now, you're assuming that the number of resources that you have is not bounded. Number of people that are requesting is also large enough. It's not impacting this, but it would be very nice to see also do it one randomly. Because right now you're changing the size, for example, capacity 2, 4, 6, 8. Doesn't mean that all the time you're going to have 2, 4, 6, 8. Is it?
Yeah, that's
Okay. But
so.
we haven't done it, but I think at some point we have to do it.
Yeah, we can also do it that way. We can do it that kind of analysis. So the next thing is we also vary the batch period. So as I said, the batch period is the time that is allowed for the request to be submitted to the system. So we vary that from 5 seconds, 10 seconds, 30 seconds, 60 seconds, and then 120 seconds. So as you can see on for the profit figure, the amount of profit that is being generated when we increase the batch size is not changing significantly. The amount of profit that is generated when we increase the batch size is not changing significantly. And then if you look closely, after 30 seconds, I don't know whether you'll be able to see, but if you look closely, after 30 seconds, the amount of profit that is generated is decreasing. And 30 seconds is the default batch period. So the influence from this part is when you are increasing the batch period, more requests are being submitted within a given batch period, and then vehicles have to provide services to those requests. So vehicles have to pick up more requests, and therefore the waiting time. You remember we put a constraint on the waiting time. The waiting time of each of the passenger or the request is also going to be affected, and that is going to lead to requests being rejected. So that will also impact or affect the amount of profit that the vehicle or the driver is going to make. And then for the response time, as you are increasing the batch period from 510 to 120, the response time for the other algorithms is also increasing accordingly. Because, as I said, if you have higher batch period, you have more requests that are being submitted. That means you have to do more processing. And so it's going to take you a large amount of time to do the processing. So that explains why the response time for all the algorithms is also increasing. But that of the multiple batch assignment methods, which is the red one, the RTV, and then the automatic schedule pool algorithm, which is the black one, those ones are increasing almost exponentially. So to move on, we also evaluated the performance of the algorithms based on the problem size. So if we increase the problem size, how will the algorithm be able to handle the increment in the problem size? So we consider a problem size where we have the number of requests to be 400,000, the number of vehicles to be 2,000, the number of requests is 600,000, the number of vehicles is 2,800, number of requests is 800,000, the number of vehicles is 3,600. So when we increase the problem size, as expected, the amount of profit that will be generated will also be increasing because you have more vehicles and you have more requests to provide services to. And then the response time or the computational time of the algorithms is also increasing. But that of the OSP, which is the state-of-the-art method, is increasing way faster than our own method, which is a single request and batch assignment with travel time assignment method.
May I also ask a question?
Okay.
How did you do the assignment of increasing the number of requests, number of vehicles, so on and so forth? In one you said 2,000 something, 3,000 something. It is not random. This number that
This is based on
you pick based on some criteria. How did you pick them?
So it's actually based on literature. So it's based on literature. You check the effect on the algorithms when you are varying each of these parameters. So to ensure that we are providing a fair comparison, we use those same values.
Because one may say that, but however you are picking, maybe it is your pricing against the state of the art multiple batch that you're saying. You know,
So those are the values they use. So
okay,
so we've not biased against them.
okay.
So finally, we considered a very large instance scale. So this one, let me give credit to Dr. Mwefa. He suggested we test something like this. And then when we did it, we obtained a very meaningful result. So we wanted to show that for each of these algorithms, are they really scalable? So we considered a very large problem size, with the number of requests being over 1 million, and then the number of vehicles that can provide services to the request being like 10,000. So when we did the experiment, we realized that the OSP, the optimal schedule pool algorithm, is the time or its computational time or is very computationally expensive. It takes a very long time, over 2,000 seconds, to provide the optimal assignment of the request to vehicles. So here we are using this approach to test for the scalability of the algorithms. And as you can see, as the problem size becomes very large, the RTV and then the OSP, which are the multiple batch assignment methods, are suffering seriously. So in the various experiment results that I showed, you realize that the profit that is generated by the optimal schedule pool algorithm, which is a state-of-the-art method, is more than, or the state-of-the-art method outperform our method in terms of the amount of profit that is generated. So we wanted to check for the statistical significance or statistical difference between the amount of profit generated by the state-of-the-art method and then our method. So we use a certain technique that is often used in the literature, and then that is also often used when it comes to this particular work, which is called Kolmogorov-Smirnov test, which is a non-parametric test for finding the statistical difference between two distributions. And here, the metric is that if the p-value is less than 0.05, we reject the hypothesis. Otherwise, we keep it. So our null hypothesis is that there is no significant, statistically significant difference in the profit performance of our method, which is the SRBAT, and then OSP, which is the optimal schedule pool algorithm. And then the computed p-value was 0.7714, which is greater than the 0.05. Therefore, the null hypothesis is not rejected, which implies that there's really no statistically significant difference in the profit performance of the state-of-the-art method and then our method, which is the SRBAT. So these are some miscellaneous some other things that we've done that we've not shown in this presentation, but if you are interested in the contact, I can share them with you. So we also evaluated the proposed framework based on the following metrics: the mean of the number of passengers in the vehicle, and then the number of late arrivals expressed, which we express as a percentage, and then the total distance that each vehicle will also travel. And then we also proved that the proposed framework is able to provide the optimal assignment of the request to vehicles. So in conclusion, we formulated the ride-sharing problem as a profit-aware problem that dynamically computes the fare per request. And then we proposed an efficient vehicle dispatch framework for on-demand ride-sharing. And then we incorporated a feasible schedule pooling strategy, which helps to improve the performance and then the efficiency of the proposed method. And our experimental results indicated that the proposed framework achieves comparable performance with the state-of-the-art vehicle dispatch framework. And the proposed framework is more than 20 times faster than the state-of-the-art vehicle dispatch framework for large instance scale when you consider the number of requests to be over 1 million and the number of vehicles to be 10,000. So in future, we want to extend this work to a distributed approach. So what we are going to do in future is, given a large city, like New York City or like Greensboro, we split the large city into different zones. So in this slide, for instance, the city has been we've grouped the city into 2 zones, zone 1 and then zone 2. And then within each zone, we are finding the assignment of requests to vehicles. And then we find the best route or the shortest route to pick up and then drop off the request. So this work, there have been a lot of people who have contributed to this work to bring it to its current state. So I would like to express my gratitude to the following people who contributed immensely to this work. One is Dr. Omefa, Dr. Shunyon, Dr. Yen, Dr. Karimudini, Dr. Bedada, Dr. Tansen. And then Stacy also helped in editing the manuscript. And then I also like to thank the whole team of ACIT, because every week we do presentation, people provide their feedback, and it's based on that feedback that we keep modifying our work to make our work better. So these are some references, and then thank you for your time and thank you for attending my presentation. And if you have any questions or suggestions or anything, and then I also like to North Carolina Department of Transportation for providing funding for this research.
Any question for him? I have many questions.
Okay.
I was hoping that you're going to at least show the optimality. Also, theoretically, you have shown that this technique is scalable. And then computational cost, I think those are very important, because it is related to the problem that you are bringing about. You didn't tell us why you think your method is good, and why do you think that your method is beating the result that you have. To me, is counterintuitive. In what way? I'll tell you why your result is counterintuitive. Multiple batch versus single batch assignment. To me, it's going to take a single batch assignment for a number of people that are in view one-to-one, where it's going to take more time than assigning, for example, 3 requests all at once to one vehicle. Why do you think that your method did better?
So one of the
What do you remember? That you're going to be also having your proposal defense soon. But those are the important things that I think it is worthy of telling people why. Those are the things that you did. Pruning, you have done some pruning. Remember that you mentioned, but you didn't emphasize to me those are. You better tell them that why your method is better. You mentioned experimentally, but I think they should know why. And also, what is so good about why did you pick that one as a state of the art? And then also, at least briefly introduce some of the characteristics of the state of the art method. Because otherwise, you're just saying something. Okay, any feedback for Ben? Any feedback? Yes.
It was a great presentation as always, Ben.
Yeah.
You really know how to captivate everybody in your presentations. So, I mean, there was a lot going on in there, so I'm not claiming that I understand the question. So maybe my question might not be quite relevant.
it's too relevant.
But I think was on slide 26, you had your graph comparing the request to vehicle 25, I think. Yeah. So is there a reason, like, how do you increase the number of requests versus your vehicles available? Is there a scale like that you're using to increase the number? Does that affect the performance? Because you say it's 4,000 K requests and 2,000 vehicles and versus 600 K and 2,800 vehicles, right? So do you have any metrics as to how you're coming up with these numbers? Or?
Yeah, that's a good question. So we are not using any metrics, or we are not using any scale or any ratio or factor or something that is similar to the question Dr. Omefa was asking. So we are using this this instance scale because this instance scale has also been used by the methods that we are comparing our method to. So to ensure a fair comparison, that's why we are using this this scale. Yeah, so we just wanted to ensure that we are showing a fair comparison between our method and then the state of the art method. So this is how these are the number of requests and then the number of vehicles that they considered in their work. And then there is no, these values are somehow generated randomly. It's not like there is a factor.
Scale,
No, there's no scale.
constant
No.
ratio.
But you just want to see how the algorithms are going to respond when you are varying the problem size. How are the various algorithms going to respond? So the focus is not on. The focus is on. There is actually an increment from one point to another. So like the number of requests has been increased from 400,000 to 600,000. So you can say the number of requests from 400 to 500. And then you also check the response of the algorithm. But we want to, okay.
So when you're conducting these experiments, are you keeping the other parameters at a constant?
Constantly, I will give the other parameter.
So what would you say the batch period for these experiments?
So this is 30 seconds.
30?